Hi everyone, I'm Hong Yi and this is Ping. We're both from the data platform team at OpenAI, and we're very excited today here to talk about our Airflow journey at OpenAI, including like what we've been built and what we've learned and things like what we do to how to get the Airflow evolved at OpenAI. Before joining OpenAI, I spent 4 years at Apple, was also the part of the Airflow team. And actually, I was also speaker for the Airflow Summit last year when I was at Apple. And Ping, do you want to briefly introduce yourself?
Yeah, hi everyone, this is Ping. I joined OpenAI very recently. Before I joined OpenAI, I was in Airbnb's Airflow team for past around 7 years.
All right, so here's the agenda. What we're gonna cover today is I will start with an overview of how OpenAI uses Airflow, basically our history, and then we will talk about some challenges we encountered. After that, we'll let Ping to take over to walk you through how we improve reliability and scaling. And after that, I would come back and talk about some toolings that we built and what we think will be the next step for us. Okay, so when I joined OpenAI, which is about a years ago, this is how I feel. Like I'm guessing maybe why it's an AI company, maybe infrastructures, the Airflow here was something like a science fiction where the clusters would be able to heal themselves and the schedulers, processors can just figure out what's the best configuration to use to best optimize the performance and maybe if anything fell that the task would be able to debug itself and just help user to make the change. But I think looking at everybody here in this room, like so many people, thank you. I'm guessing many of you have the similar curiosity or imaginations like, well, how does OpenAI operate the wrong Airflow? And the truth is, it feels very familiar. We had the same issues, facing the same kind of like challenges, like every fast-moving companies, organizations, like small fires and a noisy neighbor running along backfields and service restarts and kill some jobs and scaling problems. And honestly, this is kind of reassuring that even at a AI company, that building a good infrastructure, orchestration layer still take time, iterations, and good solid engineering work. So if we look at early days, so how early? 2023. So we're a startup. So at that time, things were pretty fluid. Like we have different teams. They're using different toolings for orchestration. Some went with Dexter, and many others just wrote things in notebooks. So that kind of flexibilities was great for people to get ideas off the ground, right? But when it comes of productionize to make it a production workflow and things start to get a bit messy. So there isn't a consistent way for people to, consolidate the source of pipelines and to review code, to testing, to deploy things in a safe way. And that leads us to a clear conclusion that we do need to invest in a unified orchestration layer. So we made a shift to standardize on Airflow to bring the workflow into GitHub and applying the general software practices like code reviews, testing. So the first Airflow clusters we've launched was in early or mid 2023. By early 2024, and that's the time we really start to see adoption take off. And we have Databricks, Spark jobs, dbt workflows, and many other things starting to flowing through Airflow. And in May this year, we deprecated Azure Data Factory, which is the managed Airflow. And 1 month later, we also shut down, sunset the Daster. So these two are pretty big milestone to ourselves, not just because we clean up some legacy system, but we, as a company, align on a single orchestration layer that we know what we should invest our resources on next. Unlike many other big tech companies, even today at OpenAI, we don't have a dedicated Airflow team. So you will just see like maybe 20-something data platform engineers working on data orchestration, ingestions, compute, storages, and sometimes even networking, Kubernetes stuff. So we have to be smart about allocating the resources. We have to focusing on what matter the most. So this year, one thing we've done, if you see here, is like we launched a couple of self-serving toolings, which I will talk about a bit more later today, to help engineers, users to iterate their Airflow DAG faster and run backfill safely early. And also early this year, we decided to double down on reliability and observability. So to have a better metrics tracking, adding some smart retries, and get better, clear user task signals to make things easier as a platform to operate. So, and about 2 months ago, we launched a multiple cluster, and today we are running total about 7,000 DAGs across all of them, and the number is still growing fast. So to recap, so Airflow has gone far from something that teams would like to try it out to something today that many teams, organizations rely on their day-to-day work. So as engineers in the data platform teams, what I feel is like there's so many questions being asked in Slack, and then sometimes I have to wake up at midnight because Airflow scheduler lose heartbeat. So that's where I get a sense of how important this is to user. I don't really enjoy that. So next, let me talk a bit about the challenges. So I will group them into 3 broad categories. So first one is reliability at scale. So Airflow has become the central of a lot of critical workflows. As I said, it was used by probably almost every single teams at OpenAI. And if that means even the small infrastructure issues could cause a production impact to many teams like finance, research, and analytics. So what we've seen the most is like tasks were just failing unexpectedly for some transient errors, and sometimes like people report that their tasks get delayed, and ourselves, we're sometimes seeing like the clusters unhealthy restarting. And so a lot of times the things happens and user and ourselves does not necessarily know what's the cause. It was like a code change needs to be made or something goes wrong in the production environment. But the goal here is we want to keep things stable. And that's how we win trust from our user. But also, that was also the hardest things that we've been facing. The second one is performance. So as the number of DAGs grows and we start to hitting some bottlenecks in here and there where was totally working fine before. So example being like the scheduler throughput and DB connections, even we use PG Bouncer, and also see like the file IOs are slow. So all these together has slowed down, not just task scheduling, but also the development cycle where user rely on to test and deploy things. The last one is simplicity. So Airflow is powerful. I think we all agree on that. But that power also comes with complexity. So users often have to, learn to understand job status, what cluster to use, and workers' capacities, and concurrency setting I should put. So even just troubleshooting a very basic issues like understand the scheduler intervals, it would take them a lot of times. And many of the time they just come to us and send us a Slack image. So what we want to do is to empower them, to provide them an easy way for them to test things locally, independently, to help them to run backfills easily, safely, without having to coordinate with the infra team. So that's the last point here. To summarize, our goal is to, 1, make Airflow more reliable, more scalable, and 2, easier to operate without, easier to use without increasing the operational burden. To kick things off, now Ping will walk through what we did to improve reliability and scaling.
Thanks, Howie. Yeah, this is Ping. I joined OpenAI recently, so I will go over some work we did to improve the overall Airflow reliability. As all we know, I believe edge cases define the reliability. As the infra team, we often get reach out when things do not go well. And recently, we identified a few interesting edge cases, and we would like to share them. So first is our user repeatedly reported their sensor get a random mark as failed, even the success criteria was met. Users also confused about the state mismatch error in the event log tab. It's really hard for them to fully understand what it means. And what they can do is also very limited. They can only just reach out to our channel or they clear their tasks. And after some digging, the root cause we identify is that a Kubernetes pod can receive a sick term at any point in time during the task execution lifecycle. For example, if a sick term is hit to the pod after the salary worker forks the task process before the task supervisor process starts, in this case, the executor records a state mismatch event. The task never gets to report its real state, and the task could be marked as either failed or up for retry. There's another interesting timing. Is after the task execution function finish, but before the task success callback finishes. If a sick turn occurs here, the task is incorrectly marked as failed, even though the work was already done. This is the problem become more visible when the success callback is slow. The longer it takes, the higher the chance it will be interrupted. And in our case, even though the census poke criteria was met, but the task was still failed due to this. There's also another really annoying edge case that the user frequently complain about. Their tasks sometimes get marked as failed, like without any logs at all in the web UI. From their perspective, it's extremely frustrating. They can't even tell whether the task actually started or crashed instantly or never run at all. So the root cause for this one is the pod is killed forcibly after the termination grace period. So by default, the salary worker finish all current executing tasks before it actually terminates. However, the pod can only wait at most the termination grace period before being forcibly deleted. If this happens, the Airflow log handler does not have a chance to upload the log to the remote storage. Therefore, the log won't be visible in the UI, and the task running inside the pod will be treated as zombie task as well by the scheduler. So now that we know the root cause for those edge cases, how do we improve the task resilience? So we first introduce a pre-stop hook in the Airflow worker pod to send signals directly to Airflow supervisor process instead of sending to the Airflow's salary master process when the pod is on kill. So in this way, the Airflow task process has a chance to gracefully shut down, uploading logs and other stuff. We also add a auto-infra retry policy. Airflow task will be auto-retried if the failure is categorized due to Airflow infra failure, which includes any signal sent to the pod and any executor events happens in the scheduler, and also the zombie task, because we believe for those cases, users should not do any manual work. We should auto-heal for them. So now the failure from the infra now is auto-healing, and rather than cascading to manual ops from the user. But there's also another interesting case on top of that. We introduced the task idempotency key to avoid unnecessary task job rerun due to Airflow task retries. So each Airflow task is assigned with an idempotency key, which is associated with a Spark job. For Spark workloads, we also introduce a on-kill behavior in our Spark operator. So when Airflow signals a task to stop, the operator now checks for the reasons. If the stop isn't user-initiated or timeout, the operator does not cancel any running Spark job. That means the Spark job keeps running safely on the cluster. And even if the Airflow worker part died, on the next retry, the Airflow task uses the idempotency key to reattach to the same Spark job instead of starting a new one. This avoids any wasted compute, duplicated jobs, and ensure the task retries are idempotent and efficient. We have one more worker part could be restarted due to Airflow infra deployments, leading to disruption to Airflow work tasks. We wanted to minimize the impact of that. To solve the issue, we designed a new Kubernetes CRD. We named it as Airflow Worker Pool, and it created a Kubernetes operator, which managed the lifecycle of Airflow Worker deployments. We changed the Airflow Worker deployment kind from stateful set to this Airflow Worker Pool. So when a new resource is submitted, this Airflow Worker operator will create a new deployment with the new name. We'll append the revision number to the name. As you can see in the bottom right screenshot, you can see the revision 1, revision 2, and revision 3. And the Airflow Worker operator runs a reconciliation loop. On each loop, it gets all current Airflow Worker deployment revisions in a namespace. It pauses the celery master process on each part belonging to the non-current revision deployment, as we need to recycle those deployments. So we don't want any new task being picked up by those workers. So in the bottom left case, you can see there are 2 revisions. Revision 2 is active, but revision 1 is not. So the celery master in the revision 1 is paused. Next, the operator checks the number of running tasks on each pod. If there's no task running inside a pod, the operator just bump the pod deletion cost of that pod and decrease the replica number by 1, so that the Kubernetes will handle the pod deletion by itself, view sorting the pod deletion cost. And with this CRD, the running pods have more time to wait for Airflow tasks to finish without blocking the new Airflow infra deployment. And in this way, even the deployment will not cause task disruption. So next, let me talk about how we scale Airflow at OpenAI. Now that so one bottleneck we discovered was that our DAG processor pod was not keeping up. Even after scaling to more pods, the newly deployed DAG will take a long time to show up in the Airflow UI. After digging in, we found that root cause wasn't due to CPU or memory. It was I/O latency from the underlying PVC. Our DAGs are stored in the Azure storage account and synced from the CI. So each pod mounts the PVC to read those files. The problem is Azure storage performs poorly with many small files. So to fix this, we deploy a daemon set called DAG Roller. It periodically downloads the DAG files from the storage account to a local host path mounted on each node. Then each Airflow pod simply mounts its local path so that it has fast node local access. After rolling this out, the DAG parsing latency drops dramatically. As we scale up, we start to hit the ceiling of a single Airflow cluster. So once we reach out a few thousand concurrent tasks, cluster become unstable, as Howie mentioned. The task began to fail intermediately due to database connectivity error, even though we already have the PG bouncer enabled, and we also disable the local connection pool in all components and Airflow tasks as well. The scheduler started to show significant delays. The task was not scheduled, even though the multi-scheduled pods running. So at this scale, we think it's that a database, Airflow database, was the shared bottleneck, and I am glad that Airflow 3 now is removed this. Everything can be scheduled with the API, which is great. So to unblock us at that time, we have to shard our cluster to use multi-cluster sharding. So we split the workload across cluster to keep one within a stable operating range. So as of now, we have 3 clusters. We might focus on building some layers to manage them seamlessly. With that, let me hand it over to Howie to talk about our toolings.
All right, don't want to miss that. Thank you, Ping. Tooling defines efficiency. I like that. So far, we have covered reliability and scaling. So next, let's talk about the third pillar, which is self-serve tooling. So the goal here was not to build a fancy dashboard or adding automations for its own sake, but to make the Airflow easier to use, safe to experiment, and simpler for us to operate day to day. So let me walk through some of the toolings that we built in the past few months. So first is the local dev tool. So one of the longest loop for many of our Airflow users is they have to writing a DAG, push that code change to GitHub, and get a review, deploy, and realize there's a bug, and now they have to repeat all the above steps. So we built a CLI tools, let's just call it Airflow Local. So these will let users to using a CLI command to start a virtual environment locally, and then install the dependencies, triggering the build of an image, and then it will upload the image, and then also push the local user's local code repo to remote blob storage. And at the very end, it will trigger the native Airflow test run commands to launch the task in a Kubernetes pod. Okay, so I know this is a bit long, but altogether, so this would form a tighter developer loop so that the users can verify their changes from their local in a few minutes, and also without having to touch any production clusters or Airflow scheduler. Next, I want to talk about the custom backfill. So we know backfills are powerful, but they can be risky sometimes, and because they hit productions, and they will sometimes trigger a lot of concurrent run at the same time, require some good judgment. So, and also we know there are more than one ways to run backfills, right? Like you can clear tasks from the UI, you can run the backfill command, and it's hard for user to know what's the best choices. So what we do is to add a wrapper from Airflow and some commonly used operators. For example, the one we use to trigger Spark job, the one we use to run DBT jobs. But to user, now they have just a single interfaces, and this will help them to configure some default settings and adding some guardrails. It will validate the user settings first and checking the resources and ask user about how they want to shard or parallel the backfills, and eventually it will automatically route the backfill job to the right pool or instance pool, so that for the users, they themselves can safely reprocess data with confidence. And from our side, we don't have to ask them to coordinate, worry that they could blow up the entire clusters or being the noisy neighbor. That's pretty much about the backfill. The third one I want to talk about is a Slack bot. So a lot of times, as I mentioned, users see their pipelines not working or slowing down, and they will just come to us asking, hey, why my DAG's stuck in queue states? And sometimes people just, at our companies just want to have a quick answer. So instead of digging into the root cause from Airflow UI to see the logs and to see other metrics dashboard here and there, like we built something like a lightweight Slack bot. So the bot will be able to get access to the job status, the log, and also you will be able to join in some metadata to help better understand what's the current status. And internally, we also hooked up with some runbooks that we wrote. So altogether, the bot is able to do the first round of investigation to give user a quick summary so that they have some baseline okay, probably this is what's happening. And so that also will guide them through what could be the next step. And what's really important here, I think many of you already have this question in your mind, like, is there will be an illusion? Yes, there will. So I think it's important to ensure that the bot could comfortably say, I don't know. So if it's not confident or don't have the context, it will be able to pull the right engineer teams to help investigate. Last but not least, a YAML-driven DAG generation. So I know this is probably not new. Many of you have heard this idea, or maybe you already implemented it. So the goal here is to help create and maintain Airflow DAG in a more consistent way. So we're introducing a YAML template for some commonly used data ingestion pipelines. So to user themselves, they just need to configure the YAML and tell us some basics like what's the input, output, how frequently I want to run, and ownership, and what kind of alerts you want to have, all in a declarative way. And the generator itself will be able to, at deploy time, will be able to emit a clean Airflow code and then for deployment. So that's the idea. And I know today some people would argue, hey, now like people are empowered by AI and they can just write in Airflow DAG easily. Like, why would you spend the effort to create such a YAML template, right? It's a rigid. It's not flexible. My answer here is that sometimes I think this is a reasonable trade-off. Like, two benefits. One is that we want to keep things consistent to avoid drifting, and second is don't forget, we still need someone to review the code, right? So YAML is more user-friendly. Okay, so across all these tools, the ideas are basically the same. So we want to shorten the development loop to bake some guardrails into the workflow and keep Airflow operational, scalable. So last, let me close with some things like where we're going next. So first, obviously, we need to improve reliability. I know this doesn't sound very exciting, but this is the top request from our users. The goal here is that the user hopefully would not notice any of the infrastructure incident. So what we will do is to keep investing in like scheduler health and adding more system level retries and lower the control plan latency. And to achieve those, we need to also ensure that we improve our metrics to know that we are actually heading to the right directions and making the right changes. Second one is scaling. So we are seeing usage increases growing really, really fast. So we have to target in 10x. So what we do is to building blocks that will let a single Airflow clusters to be able to serve more DAGs, schedule more workflows. In the meanwhile, we also need to build better toolings and infrastructures to help ourselves managing multiple clusters. The third one is to lower the learning curve. So basically, we want to make the platform easy to use. So backfills should be simple. Local tasks should be fast, and signals should be clear, right? A user find if it's due to a capacity issue or it's due to a bug in the code, that should be obvious to user. And also, one thing I want to highlight here is that we should not ignore the importance of keeping the documentation up to date, because that was not only used by user, and for us, it was also used by the chatbot to be able to know the latest updates, context, and serving that answer back to user. Last but not least, we're also started thinking maybe we can form a better feedback loop. So today we do have a ticketing system, but we prefer to having user to asking the question in Slack. So it's more like a cultural thing. So this will help ensure that we move faster and stay closer with the use cases. But we also need to be able to scale that kind of support, right? So that's why I think if we can somehow form like a feedback loop, like a flywheel thing, basically if a question has been answered in the Slack channel and the bot should be able to learn from it, we are thinking about to track all those conversations and to categorize, to train the bot with that so that next time it can do better. So and our engineers can spending more time, can get more time back and focusing on tasks with higher leverage. To wrap up, we still have a lot of things to do. We're still early in this journey, so I'm happy to learn and grow together with the community, and we're really excited about what's ahead.